Lesson 4 in our chapter discussing the electronic structure of an atom is titled The Wave Behavior of Matter. In our previous lessons, we've talked at great length about how wavelengths and frequency, which describes energy motion, especially for light particles, has been expanded now to talk about quantums of energy. If energy can behave as matter, can matter behave as energy? And that's really what the focus of lesson 4 is. Previous lessons have really shown evidence, both mathematical and experimental observation, that energy behaves as matter. And the proof of that came with the line spectrum work by Niels Bohr. And now with Louis de Broglie, he's going to propose that the flip side of that, matter can act as a wave. Matter, specifically in our chapter, will be the electron. Electrons have mass, and yet they do have a characteristic, all the possessions of wave functions. So in the years that followed the development of the Bohr solar system model for that hydrogen atom, that dual nature of radiant energy became a very familiar concept. Louis de Broglie, who was working on his PhD actually in Paris, boldly extended this idea by proposing that if radiant energy could, under the appropriate conditions, behave as though it were a stream of particles, could matter, again, under appropriate conditions, possibly show the properties of a wave. Would an electron orbiting the nucleus of the hydrogen atom could be thought not only as of a particle, but as a wave with a characteristic wavelength. De Broglie suggested that in the movement about the nucleus, the electron has associated with a particular wavelength, and he went on to propose that characteristic wavelength with the following mathematical formula. If we substitute the term velocity in for frequency, now notice this is mu, that Greek symbol with the kind of like the squiggly V, and V for velocity or speed. We come up with de Broglie's equation. The wavelength of matter is equal to Planck's constant over the product of mass times velocity. mv, that's what mv is going to stand for. Planck's constant is familiar to us from a previous lesson in our chapter, set over mass times velocity. Now I know in physics we've learned that mass times velocity, that product, is known as momentum. When we take a look at how these units break down, lambda, of course, which is wavelength, is measured in a meter. H, which is Planck's constant, 6.63 times 10 to the negative 34th joules times second. I need to remember that a joule, which is a metric unit of energy, is actually equivalent to 1 kilogram meter squared over second squared. Now that might be brand new for us. And of course the reason I'm putting this all in here is that notice velocity must be in a meter per second to make the joule work. Meter per second for velocity. And that mass must be in as a kilogram to align itself with the very definition of a joule. All right, and that joule is being used here in Planck's constant. So some very critical information in terms of our formula, but not only that, but the units that must go in as well. De Broglie used the term matter waves as a unit there of describing how objects behave as waves. Electrons not only behave as particles with mass, but as waves with specific wave functions and frequencies. So when we use de Broglie's equation, and again, if you have that equation page that we've been kind of using throughout the course, you might consider adding on the following. So here is from a previous lesson, the equation page we have going. One more equation where we use de Broglie's equation. So here's the speed of light equal lambda times nu, wavelength times frequency. That constant 3.0 times 10 to the 8th meters per second for the speed of light. Calculating energy uses Planck's constant times V, or the frequency. Planck's constant, 6.63 times 10 to the negative fourth joules times second. Rydberg's equation, 1 over the wavelength is equal to Rydberg's constant times the difference of n1 squared minus n2 squared reciprocaled. The last equation mathematically in our journey of the quantum mechanical model of the atom, the wavelength of matter can be found by using h, Planck's constant, set over mass times velocity. And I'll put that in a parenthesis. You might want to consider remembering the units. Planck's constant, the unit here is a joule times second. Joules times second. Mass must be in a kilogram, and velocity must be in a meter per second. This is not a constant, but it's an equivalent value. 1 joule is the same as saying 1 kilogram times meter squared per second squared. And that's a reminder of why we have to have those units in there just to make them match. Wavelength will come out in a meter when Planck's constant goes in as a joule times second. Mass is a kilogram, and velocity is meter per second. So there's that additional work on our equation page, taking a look at matter waves proposed by Louis de Broglie, calculating the wavelength of an object. Let's take a peek at how this might work. What is the wavelength of an electron moving with a speed, that's another word for velocity, speed, of 5.97 times 10 to the 6th meters per second? I like this. This is a correct unit for velocity. I can't spell. C-O-R-R is correct. And then here we're given grams, but I need to make sure that that goes in as a kilogram to calculate wavelength. Wavelength uses Planck's constant times the product of mass times velocity. We're being asked to solve for the wavelength. Planck's constant goes on the top, 6.63 times 10 to the negative 34th. Include your unit, joule times second. The mass, let's do that little conversion over here on the side. We know that to convert, it's a simple slide of the decimal, but I'll show it. Here is the mass given to us, 9.11 times 10 to the negative 28th grams. We want the gram unit to cancel, and we want to go to the kilogram. 1 kilogram is equivalent to saying 1,000 grams. So if you slide your decimal by dividing by 1,000, 28, 29, 30, 31, so that's 3 spots to the left. We get our equivalent value, 9.11 times 10 to the negative 31 kilograms. And luckily we were given the meter per second velocity or speed, so that can go directly in there, 5.97 times 10 to the 6 meters per second. We calculate this out, the units simplify to give us meters. And let's do that, shall we? Let's give myself a little more room. Calculate the wavelength that will come out in a meter. So I start by hitting 6.63 e negative 34 divided by, and then use a parenthesis so you get the correct answer, 9.11 e negative 31 times 5.97 E6. 5.97 E6 was the velocity given to us. Is that correct? Let me just be sure I'm hitting that in right. Yep, 5.97 E6. Close your parenthesis and equal. This wavelength comes out to be 1.22, we'll say, times 10 to the negative 10th meters. You might also see that reported as 0.122 nanometers, nano being 10 to the negative ninth. It's just the common unit given to a wavelength in that particular region. Make the number a little bit more manageable. So we calculated the wavelength of an electron, even though it has a mass, which is a characteristic of a physical object, a matter, but it also behaves as a wave, a little packet of energy. This number here, mass of an electron, it's actually worth writing on your equation page because oftentimes in the homework spot, you're going to be asked to know that or to look it up. Continuously looking it up gets to be a little tedious. So if I were you, I would put on my equation page the mass of an electron and I would record it as a kilogram since you're going to have to convert it anyway. Mass of an electron, 9.11 times 10 to the negative 31 kilograms. That way you've got that standard and don't have to look it up again. Let's see what another example might look like. Using the de Broglie relationship, which is simply wavelength is equal to Planck's constant over momentum, mass times velocity. Use this relationship to determine the wavelengths of the following objects. We have an 85 kilogram person skiing at a 50 kilometers per hour. So here's what I like with this one. I have the correct mass, but I have the wrong units for velocity. Velocity has to be meter per second. So we'll have some conversions there. We have a 10-gram bullet at 250 meter per second. Okay, so this is the conversion here. This has to be a kilogram, but velocity looks good. And what I'm referring to is this has to be kilogram. This must be meter per second to make the units gel. And so forth. So let's take a peek. We have a lithium atom. So this will incorporate looking up a weight off the periodic table. Let's start with this, we'll call letter A. An 85 kilogram person skiing 50 kilometers per hour. What I'm going to do first is get my kilometer per hour into a correct unit, meter per second. So I'm just going to do some conversion factors. I know that if I have a kilo, I need that to cancel, and I need to go to a meter. 1 kilometer is 1,000 meters. Kilo, of course, is 1,000. So there's that canceled, and I've got the meter unit I desire. Now I have per hour, and I need that to get to a second. So, okay, I need hour to cancel, so it has to be the opposite side. 1 hour is 60 minutes. I don't know how many seconds, so I have to do two conversions here. And I know that a minute is 60 seconds. So let's see if I've got kilometers gone, have my desired meter for the top. I've got hours gone and minutes gone, and what's left? Meter per second. So all I have to do is to calculate. I need to hit 50 times 1,000, divide by 60, divide by 60. And I've correctly converted into my desired unit there of meter per second, which I get 13.88 repeating. So let's say it's 13.89 meters per second. Alrighty, so now I have that correct unit. Mass is in the correct unit. Let's solve for wavelength. Wavelength is equal to Planck's constant, 6.63 times 10 to the negative 34th, and that's a joule times second. Mass is correctly given as a kilogram, so we left that value alone. And now I have my velocity in the desired unit of meter per second. Units will then cancel. Remember, it's the joule that's making us have kilograms, meters, and seconds to get all the units to gel. And let's hit that out. Let's start by hitting Planck's constant, 6.63 E negative 34 divided by parenthesis 85 times 13.89. Close that parenthesis. We get an extremely small wavelength, which makes sense. 5.62 times 10 to the negative 37th power meters. Could we, with our normal vision, see that small of a wavelength? And the answer is absolutely not. The larger the object, the smaller the wavelength. Therefore, it's undetectable with our naked eye. The tinier the object, the longer the wavelength, and we're going to be able to see that in a microscopic world, not in the macroscopic world. Let's try letter B. We have a 10-gram bullet being fired from a gun, 250 meters per second. I said we liked the meter per second. That's fine to go, but I do have to do a little conversion here to get grams into kilograms. So I want gram to cancel, and I want to go to a kilogram. I understand that a kilo is 1,000 grams. So just simply taking 10 divided by 1,000, and you come up with 0.01 kilograms. And that's the unit we need for mass. So let's solve for that wavelength of a bullet. Alrighty, using Planck's constant, 6.63 times 10 to the negative 34th joules times seconds over the mass, and now the correct unit for that bullet is a kilogram. And the velocity that was given to us, 250 meters per second. Simplify this expression, we'll have wavelength in a meter. Start by hitting with Planck's constant. Divide by the product of 0.01 times 250. That means use parentheses. And we found an answer here of 2.65 times 10 to the negative 34th meters. Notice we went from 37th, a smaller number, to 34th, a slightly larger number, but still impossible to see with the naked eye that small of a wavelength. But what about a lithium atom? Well, first of all, we got a little work to do here with the periodic table. We have a velocity given to us, which is nice. The unit matches meters per second, so that's good for velocity. But they really didn't do much with the weight, a lithium atom. So how much would one atom of lithium weigh? So I go to my periodic table, and you might have one handy, and let's find the molar mass of a lithium. Molar mass, I'm going to call that 6.9 grams. 6.9. But remember that molar mass is how much one whole mole weighs. 1 mole of lithium has a weight of 6.9 grams. It's a very definition of molar mass. Avogadro's number of atoms of lithium equals 6.9 grams. See what I'm doing here is just kind of remind us of when I look up a weight on the periodic table, it's telling us if I had a whole mole of them. Well, I don't. I want just the weight of one lithium atom. So let's just take a little proportion. I want the weight of one atom. So here I have 1 atom of lithium, and let's use this conversion. I want atoms to cancel. I want to land at a gram. In a whole mole's worth, which is an Avogadro's number of lithium atoms, it would weigh 6.9 grams. That's like an old mole map conversion, isn't it? Atoms cancels and it brings us to the gram unit. And it's going to be quite small. I mean, how much would a lithium atom weigh? It would be quite insignificant. 1 divide by Avogadro, 6.02 E23. And we get a number. I have on my screen 1.66 times 10 to the negative 24th grams of lithium. Oh, I need that to be a kilogram, don't I? So you can just simply slide that, but I can show the conversion. Here's the gram unit. We want gram to cancel, and remember for this de Broglie equation we must have kilograms. So here we know that a kilogram is 1,000 grams. So really just sliding the decimal 3 more spots to the left, but you can prove that to yourself. Simply divide by 1,000, and now do you see how we have 1.66 times 10 to the negative 27th kilograms as the mass of a single atom of lithium. All of this work, we had to find the mass in kilograms of a lithium atom. Not a whole mole of lithium atoms, but a single tiny one individual particle. We started with the molar mass and turned it into the mass of a single lithium atom measured in kilograms. Now we have the ammunition to find the wavelength of that lithium atom. We do that by using Planck's constant, 6.63 times 10 to the negative 34th joule times second. We use the momentum on the bottom, which is the kilogram we just calculated, times the velocity in a meter per second, which, let me scroll back up, I forgot it, 2.5 times 10 to the 5th meter per second. All right, so the product here is called momentum. Planck's constant divided by the momentum. And let's hit for a common answer. 6.63 e negative 34 divided by the product, means use parentheses, the product of 1.66 e negative 27 times 2.5 e5. Close your parenthesis. In this wavelength, 1.597, I should round better, 1.60 times 10 to the negative 12th meters. You might want to slide that into nanometers, but this would be fine. And I just want you to take a notice of as the size of the object gets smaller. We have a very large object, an incredibly small wavelength. By the time we get to a tiny, tiny, tiny atom, the wavelength becomes much more observable in the microscopic level, a magnitude that's much larger. Longer wavelength, smaller object. We have that inverse relationship. So we were looking at really just verifying that electrons travel as not only energy packets, but also as matter, the dual nature of energy and the dual nature of matter. One last slide, and it's just going to end up to be a margin note for you. I'd like to define the uncertainty principle. This will be a homework question, and I didn't make your note pack, but it's definitely worth defining. I want to talk a little bit about something called the Heisenberg uncertainty principle. Just a small little footnote, but worth mentioning so that homework question becomes a little bit easier. Werner Heisenberg, he's a German physicist who was proposing that the dual nature of matter places fundamental limitations on how precisely can we know the location and the momentum of any object at a specific snapshot in time. So this is what's known as the Heisenberg's uncertainty principle. When it's applied to the electron in an atom, it simply states that it is impossible for us to know simultaneously both the exact momentum of an electron and its exact location in space. The Heisenberg's uncertainty principle you'll be asked to define. It is impossible to know simultaneously, both at the same time, correct? Simultaneously, both the exact momentum and the exact location, of an electron in space. Whoops, I keep hitting the wrong button. That's an in space. So mathematically related, he's simply reminding us that we can slow down an object to locate it, or we can speed up the object and not know where it is. So it really is impossible. If you think about mass times velocity, that term momentum. The heavier the object is, the shorter the wavelength, and therefore it's impossible to kind of identify the location. And this will wrap up the lesson 4 on looking at electronic structures of atoms as matter waves, the waves of behavior in terms of both particle and energy. Friends, you're going to proceed now to complete your lesson 3 and 4 combined homework. When that's completed, I want you to move on to try the multiple choice lesson 3 and 4 combined quiz.